Hello everybody, and welcome to another lecture. We've talked about root finding for bisection method and the method of false position. Now it turns out that these methods are a little bit slow compared to some methods that are out there. So this lecture and the one after, the next one, are going to talk about some more powerful, more efficient methods of root finding in the secant method and Newton's method. These are really, really important. They're more useful, and so we're going to be covering them. So let's get into it. Yeah, we're going to start with the secant method for today. And the secant method is, we've already got a little bit of some knowledge about methods that use secant lines. The method of false position was a really good introduction for that, and it's going to help us with some understanding here. So there's a difference though. The first two methods that we talked about, we obtained an interval at every step that brackets the root. And so every single time that we iterate the process, we ensure that the root is somewhere between our two estimates, the two ends of an interval so far, in order to produce a new smaller interval and so on. Yeah, but the thing is that there are other methods, and the one that we talk about today, and the one that we talk about in the next video, don't use intervals. And we don't do a special step to check to make sure that a root is bracketed, like that we have one side of the interval and one positive or negative, and the other side of the interval on the other. That's not going to be in play anymore. And these sorts of considerations can greatly speed up the process. There are some caveats, and I'm going to show you what those caveats are, but there's a lot of potential there. The secant method, as I said, it works a lot like the method of false position, but it does something a little bit different. It relies only upon a best estimate of a root of a function f at every step. We don't need a bracketing interval each time, and in fact, our estimates do not have to be on either side of the root. And because we don't check, that helps to speed up the calculations a lot. The difference is that we need two initial estimates of the root, so x0 and x1 to start with. You got to make sure that they're close enough to the root, or the method might not converge. That's a little bit different than what we're used to, but I'm going to show you very directly why that might be. Yeah, so let's talk about the different steps that we need. We need two initial estimates, as I said. So hopefully close to the root. Okay, what we do once we have those estimates is that we draw a secant line connecting the 2 points in the graph, x0, f of x0, and x1, f of x1. You find the x-intercept of whatever that secant line. That x-intercept is going to be your next estimate. And then you toss away the estimate from 2 ago, and you use the most recent 2 in order to do the same process over again. So you repeat the process, and you always use the 2 most recent estimates to get the next one. It turns out that this works, usually. And we're going to see what's happening in this next picture. So I'm going to do one demonstration of how it works, and then another of how it doesn't. And so I want to go over that with you. So let's see here. Suppose we have two estimates to start with. I'm going to start with x0 right here at 0, and let's say x1 is right here. Okay, our job is to try and estimate this point here. That's the true root. That red point right there is the root of this function. I don't even know what the function is, but that's not the important part. I can still draw secant lines and stuff. I can see that x0 f of x0 happens right about there, and x1 f of x1 happens right about there, and the secant line connecting the two, connects those 2 points, giving me a new point, an x2, that looks like it's right about, here. Here, I'll draw a tick just like I did before. That would be my x2. And then from that, I can take a new x2, f of x2, which looks like it's going to be right about there. And I can use that to create a new secant line. And you see how this is going to work. I don't worry about x0 anymore, and I just use the information about x1, f of x1, and x2 f of x2. The secant line connecting those two is the line that goes through those 2 points, and I've drawn that there with a dotted line. You can already see how close we are. x3 looks like it's right about here now. Whoops, draw that in blue. Right about here. And then we could use that point to get even closer. And you can continue that. If I found the secant line there, it would be super close, the intercept of that line, to the true root in red. So you can see how those successive estimates are coming right in towards that root really, really quickly, even though our very first two estimates were on one side of the root, so they didn't bracket. Now, you got to be a little bit careful here. This, you can see how powerful it is just by looking at it graphically. But if your first estimates are not close enough, things can go wonky. I want to show you how that is. So I'm going to erase what I've done here. And we're going to start over, but watch what happens if you choose kind of the wrong values to start with. Suppose that we have x0 all the way the heck back here, and x1 being right about here. You might be able to see, like, I don't know why you would choose these as initial estimates if you know anything about the function, but maybe you don't know anything about it. F of x0 would be down here. F of x1 would be right here. And you can see from just drawing that first line that the secant line connecting the two is going to have an intercept that is way the heck over here. And so your next estimate's going to be far away from that root. Over here, x2, question mark, and I don't even know what the function's doing out there. So you can see that just from a simple example here, your two estimates should be close enough to that true root so that you get some sort of the behavior, right? The behavior of the function here is what's throwing this next estimate off. So you kind of have to keep in mind a little bit about that function, what its behavior is, and make sure that you're close enough. So I'm going to get rid of this for now because I've managed to demonstrate things, but for the completed notes, I'm going to refill this in with some an example that makes some sense. Okay, in any case, what's nice about this method is if you have the last two estimates, x0 and x1, calculating x2 is finding the x-intercept of a secant line. And we've already done that. We did that calculation for the last method. That's the method of false position. So our scheme is pretty much exactly the same as what we already know from the last method. It's going to use the last 2 points. So this is essentially what it looks like. X, the next estimate, is equal to minus, well, y of the last estimate, and then a ratio that gives you a slope, plus the x of the last estimate. So this follows exactly the same justification from that last lecture. If you're interested in where it comes from, go and watch that lecture really carefully. Okay, so this is the scheme that we're going to use, and we're going to jump into an example here and actually use it. So let's see what we have here. The function f of x equals x over x plus 3 minus the ln of x squared has a root somewhere in the interval minus 3 to 0. And we're going to find an estimate for it by choosing two initial guesses and performing two iterations of the secant method. So I've got some calculations here that I did in advance, but we're going to use some sort of good guesses to begin with. If the roots are somewhere in between minus 3 and 0, I see that this function actually has asymptotes at minus 3 and at 0. Just looking at it, right, ln of 0 is not defined. Minus 3 is going to put a 0 on the bottom of that function. We should probably keep our estimates in between. Let's choose minus 2 and minus 1, perhaps as good first estimates. So we will choose those. It might work for all sorts of different estimates in there. This is just a choice that I'm making. So let's use x0 equals, I said, minus 2, and x1 equal minus 1. Okay, and then let's just go for it. I'm going to need, let's see here, I'm going to need the y values associated with each one of these to put in the formula to find x2. So let's calculate f of x0 and f of x1. So f of x0 is f of minus 2, which is going to equal minus 2 over minus 2 plus 3, minus the ln of negative 2 squared is 4. So this works out to, if you do this right, I've calculated this in advance, this goes to minus 3.3863. That's enough precision for me. And we can similarly do f of x1, and that is f of negative 1, and you work that out, that's minus 1 over minus 1 plus 3, and then minus the ln of 1, which is going to be 0. You end up with just negative 0.5 from the looks of it. Okay, so I have those quantities, f of x0 right here. I have f of x1 right here, and I can find f of x2 by using that formula. To find x2, we use, let's do the calculation here. x2 equals minus f of the one before it, and then times that ratio to give you the slope, x1 minus x0, over f of x1 minus f of x0, and then you add the previous x, just like this. So slot all of that stuff in. We know what x1, x0, like we have all this information, so not too surprising how this is going to come together, but we get, yeah, what do we get here? Minus f of minus 1, and then minus 1 minus minus 2 over f of minus 1 minus the f of minus 2, and then we're going to add the previous one, and that's going to be plus negative 1, just like this. Okay, great. You put all of those different values in there. I mean, I guess I can do it, but I don't know. It's all there above, so maybe I'll just let you calculate it out. x2, you should end up here with minus 0.8267. So that's one iteration. I've now found a new estimate, x2 equals minus 0.8267. And to do one more iteration, we're going to need f of this. So, and we can calculate f of x2. So f of that negative 0.8267. If you do, you're going to end up with minus 0.8267 over minus 0.8267 plus 3 minus the ln of minus 0.8267 squared, like so, and that should work out to about 0.002375. So look at that. Our next estimate that we got, this x2, is already, it has to be something close to the root, because, I mean, the height of the function there is so close to 0 already. So we're already close to the root. Okay, and we want to do one more iteration. So to do one more iteration, find x3, and x3 is going to be given by, very similarly, minus f of x2, and then that ratio, x2 minus x1 over f of x2 minus f of x1 plus x2, and I'll let you fill out all of those values, but if you do, you're going to find that this works out to minus 0.8266. So really, really close to the last estimate, because we were so close. But this is the very best estimate that we can get. And that is, after just 2 iterations, our estimates have not even changed within, well, what? Within 1/1000th. So we've done really, really well. You can kind of see some quick convergence happening, and that's due to maybe our first estimates, as well as the nature of the function there. But it goes to showcase how powerful this is. And you can use graphing software if you want to check what the true root might be. So there are a couple of things about this method. as we saw about the that graphical example I did, I was able to demonstrate one situation where, well, obviously, our estimates were getting further away. So because the this method doesn't require the same sorts of bracketing, it's not actually guaranteed to converge, and that's part of the price of the power. Okay, but there are certain conditions under which we can be certain that the method will converge. Okay, so the convergence for secant method are guaranteed if the following hold. So first of all, we need the function to be continuous, we need its derivative to be continuous, and we need its second derivative to be continuous. So we need certain differentiability requirements on this thing. That makes sure that the function can't like suddenly jump up to something else, and it has some relatively smooth behavior within some sort of interval of the root. One more thing that we need is for the root to not have a derivative that's equal to 0 there. And I want you to see why that might be. Imagine if we had a situation where the root, let's draw the function in red, where the root was right here, and it hit a horizontal tangent right at 0. It's going to be really difficult for our estimates to converge to that root all of the time, because imagine that if I get close to that root, imagine if I have an estimate here and an estimate right here. I'll do those in blue so you can see. The secant lines are going to get increasingly horizontal, and as they become increasingly horizontal, well, look what happens. Our next estimate is going to end up being flung way the heck off into the distance, right? You're never going to be able to converge in towards that root because that increasingly horizontal secant line is going to throw your estimates way the heck off into the distance. So hopefully that makes some sense as to why this is a condition, in which case we're not guaranteed to have that. Okay, and then the last thing we saw specifically with that example I drew before, you need to make sure that x0 and x1, your initial estimates, are sufficiently close. So they have to be within some small neighborhood, and that neighborhood is going to completely depend on what kind of function you're dealing with, the nature of the root that's involved. Okay? If these things are in play, if your initial estimates are close enough, if you have that these other things are true, then you get a faster convergence than either of the methods we've come to so far. And really interestingly, it's been found that the order of convergence is actually 1.62, which is the golden ratio. So this 1 plus root 5 over 2 is a special ratio that appears here and there kind of randomly. I don't know, it's not random at all, but it's really interesting. So the convergence is much faster than linear, but it doesn't quite reach quadratic convergence, which would be faster yet. But this is a much more powerful method that lets you find those roots even quicker. Okay, so you're going to see that a lot, where we have better methods, but they come with certain reservations, as in like, oh, we don't have a guarantee this time. Bisection method is slow, but we know we're going to get to a result eventually. But secant method has some issues. Okay, so we come to coding, and coding secant method really isn't that bad either. I'm going to go through some technical details that you should think about, and then we'll go through a flowchart, and I'll let you do the coding based on the progression, right? I gave you the code for bisection method. Going to false position should be a small step forward where you just replace one line, and then that line helps to drive secant method, and so it's a small adaptation of that code. So I want you to think in terms of that sequential coding and work to get that down. Okay, here are the ingredients that we need though. We need to have the function f, so you need to be able to define that. Symbolic, again, is a good way to go. Two initial guesses, x1 and x2, you know, are hopefully somewhere near the root. I used this notation, which represents kind of a vector formulation. So you're going to need to save information from at least the last two estimates and using a vector to represent those estimates can make those quantities easier to refer to. You might just want to make sure that the variable that you're defining symbolically, like f of x, you might want to use initial guesses that don't use like the same variable here. So you might want to define the function as like f of t, and then use estimates that are x1, x2, x3 to sub in, so that the MATLAB isn't confused between what you've defined symbolically and some different things that you've designated as numbers. Okay, anyway, whatever you do, you are going to want to obtain a new estimate through the scheme for a secant method. And again, I'm going to emphasize that to make sure that your program doesn't lock up and accumulate too many symbolic things, you want to use a double command to kind of flatten and get a numerical result at each step, so you can sub things back in. So your code should look something like this, where your xn plus 1, your next estimate, is equal to, and then this is the scheme put into kind of code format, using xn as your estimates and f as the function. So this puts everything together. It's not perfect, right? There are going to be operations that you need in here, like I'll start this kind of pseudocode, but something that looks a little bit like this. Okay, and then once you've got this, you're going to want to repeat it within a loop rather, for different values of n. So repeat until some stopping criteria are reached. Either we have converged to a result, so your estimates aren't changing very much, or maybe you go a particular number of iterations. Maybe you iterate 10 times or 20 times, but secant method tends to be very quick, so you probably won't need 20 iterations. So yeah, take a look at that, try it out. Sometimes people are helped along by these flowcharts, so I provided a flowchart to you to kind of see kind of how this would flow logically. So you're going to want to start the program, initialize it with your beginning estimates. So these are your beginning estimates, and whatever your f is that you're interested in. And then once you've got those designated, you want to find x3, you want to find x4, you want to find x5. And this is going to be inside a loop, so you can keep going and going and going. So inside that loop, you're going to find the next xn plus 1 value via the scheme. And at every step, you should probably check to see if your value is, right on 0, meaning you've actually found the root. That's unlikely to happen for most functions, but you should converge to pretty close pretty quickly. But do that check to see if you've actually found the root. If you haven't, keep going if you haven't reached the maximum number of iterations, and then just repeat the process with further ends. Once you've finished, once you're within a tolerance, or once you've done enough iterations, then your last result here will be your best estimate. And you can tell if you've got a really good answer if you find f at that last estimate and you get an answer that's close to 0. So it's really not that bad to program. It uses the same tools as you've got before, but it's actually a little bit reduced in coding because of the fact you're not doing all these checks to make sure that you have bracketing. And that actually helps to speed things up. So your job is to try and code this on your own. We're going to be doing one more method, and yep, that's the end of this section of notes. So let's bring it in here. We're going to be talking about Newton's method in the next lecture, and this is also going to be one that's really related conceptually to secant method, but then is even faster and more powerful. So I would say that a good place for you to concentrate your attention is making sure that you can get this method coded. And if you've got false position already done, this should not be a huge jump. And in fact, your code should be even simpler and a little bit faster even. So enjoy. I think secant method is really powerful. It's really interesting. And I don't know, it's very gratifying when you can put together some code to make that happen. So give that a try. And when you're ready, take a look at the next video and you can see an even more powerful method. And it will be our last one that we cover explicitly in terms of root finding. So join me then. And until then, I wish you a fond farewell.